Alright, so in the last course we have talked about the circuit, right? Even though this circuit is not amplifying in voltage, since it's an emitter follower, it's very good to use in cases where current amplification is required. The problem of this circuit though was that the active device, which is the transistor, is in conduction all the time, especially when there is no input signal present. This never turning off feature of this amplifier causes a reduction of power efficiency, which means nothing else but a lot of power is wasted for nothing. You might wondering what's the point of talking about this circuit anyway, when all we wanted is to discuss about different types of amplifier. Well, as you will see, the Class B amplifier is similar to this one in the sense that both amplify only in current, but it got a huge advantage that the efficiency has increased to more than 60%. So this is a circuit that we call as Class B amplifier. The circuit also goes by the name push-pull amplifier, and you will soon understand why people call this push and pull. But I guess it's not that hard to realize just by looking at the circuit why is it called like that. So push-pull amplifier is a type of power amplifier. It contains a pair of active devices, such as a complementary pair of transistors. Here, one transistor supplies the power to the load from the positive power supply, and the other one sinks the current from the load to the ground. Without further ado, let's see how this circuit works. The input signal comes from a signal generator that outputs an AC signal of 5 volts, and the output voltage is less than 5 volts with one diode drop. What an amplifier, right? Hold on and you will see why is it so useful. So during the first positive half cycle of the signal, the two bases will become positive, right? When the positive half cycle reaches 0.7 volts, the NPN transistor will start conducting, while the PNP transistor will be reverse biased. The NPN transistor will turn on, allowing the positive half cycle to pass through, but of course the voltage of the positive half cycle will be one diode drop less because of the base emitter voltage drop. As you can see, during the positive half cycle the PNP transistor doesn't have any chance to turn on. Because let's say if the base voltage of the NPN transistor is 3 volts, the emitter will be 2.3 volts, but the emitter of the NPN transistor is also the emitter of the PNP transistor. And as we already know, the condition for the PNP transistor to turn on is that the emitter has to be with 0.7 volts higher than its base. So there is no chance for this poor PNP transistor to turn on. But no worries because the negative half cycle comes. During the negative half cycle of the signal, both bases go to negative. So now the base emitter junction of the PNP transistor is forward biased, while the NPN transistor is in cutoff mode. Alright, so again, why does this PNP transistor turn on exactly? The input signal goes up and down to negative, but let's examine it in more detail from the point when the positive half cycle goes down towards the negative half cycle. Imagine the input signal is at 0 volts right now, and if the input signal is at 0 volts, both transistors are turned off, right? So the emitter voltage of the PNP transistor as well as the emitter of the NPN transistor will sit at 0 volts too, because it is connected to ground through the load. The input signal starts going lower than 0 volts, it almost reaches minus 0.7 volts, and the emitter is still at 0 volts. The moment the input signal is equal or lower than minus 0.7 volts, the base will be lower with one diode drop than the emitter, so the PNP transistor will start turning on. Alright, I hope you understand how the circuit works right now. Even though this circuit doesn't provide voltage amplification, the output current is 100 times higher than the input current. The output current is equal to beta of the transistor, which is 100, times the base current. So if we stop the simulator during the positive half cycle of the input signal and we check the current on the base and the current on the emitter, we will see that indeed the output current is 100 times greater than the input current. Overall, Class B amplifier is much more efficient than a simple Class A, because here, if we remove the input signal, both transistors will be in cutoff mode, so they won't conduct any current whatsoever. One drawback of this push-pull amplifier is the crossover distortion. You might have noticed that there are little glitches here. In other words, the output is distorted whenever it crosses ground. Basically, this happens because during the positive half cycle, from 0 until 0.7 volts, the NPN transistor is not conducting, so the output doesn't know that the input signal has increased from 0 to 0.7 volts, right? Only by now, when the input reaches the 0.7 volts, the output will start increasing its voltage. The same problem applies for the PNP transistor. So how can we resolve this issue? Well, one solution is to keep both transistors in conduction even if there is no input signal present. And this is where class AB comes into play. Class AB, as the name implies, is a combination of class A and class B. Class AB amplifier output stage combines the advantage of the class A amplifier and the class B amplifier while minimizing the problems of low efficiency and distortion associated with them. Now, even without input signal, both transistors will conduct a small amount of current. Let's check. Without input signal, there's 197 milliamps passing through the transistor. This means that the transistor dissipates a constant power of 2 watts. That's already way better than the 35 watts of power dissipation that we have seen in the previous course. This constant power dissipation is achieved by pre-biasing the two transistors in the amplifier's output stage. Just for your information, small plastic transistor packages like the popular TO92 can dissipate a few hundred milliwatts. The metal cases like the TO18 and TO39 can dissipate more power, like several hundred milliwatts. Plastic power transistor packages like the TO220 and the TO247 dissipates well over 100 watts, approaching the dissipation of all metal TO3. So how does this circuit work anyway? The two complementary transistors are biased in order to minimize the crossover distortion, so that they are always in conduction due to this voltage divider network. I want to ask you, what is the voltage difference between this point and this point? The voltage difference between these 2 points is 20 volts, since this point is at 10 volts and this is at minus 10 volts. So there is a voltage drop starting from this resistor, another voltage drop, another one, until it reaches the minus 10 volts. Since the upper voltage divider is the same as the bottom voltage divider, the voltage in the middle is 0. So we can even connect the ground here because it won't change anything. The resistor values are chosen such that this resistance is equal to this one, and also these two resistances must be equal. When properly designed, the voltage between the two bases would be equal to 2 times base emitter voltage. This voltage drop will bring both transistors above the cutoff state. They will therefore both conduct simultaneously a portion of the input signal. If there's a voltage drop of 0.7 volts across this resistor, and since this terminal is at ground, it means that the base of the NPN transistor is higher with 0.7 volts than the emitter, which after all is connected to ground as well through the load resistor. We all know that if the base is higher than the emitter with 0.7 volts, the transistor will turn on. On the opposite side, the voltage drop across this resistance is the same, since it has the same value and also the same current is passing through it. Now, from ground until this point, there's a 0.7 voltage difference, which in turn means that the emitter, which is also at ground, is higher with 0.7 volts than the base of the PNP transistor, which is enough to turn the transistor on. Now, of course, you can play with the value of these resistances and you don't need to have a voltage difference between the two bases as high as 1.4 volts. It can be lower, and the lower you go, the more efficient this circuit gets, because if the voltage difference between the two bases is lower than 1.4 volts, the transistor will conduct less current, and so the quiescent collector and emitter current is less, which in turn means lower power dissipation on the active devices. But this comes at the expense of greater crossover distortion, So it's a compromise between quiescent output current and crossover distortion. We forgot to mention one important disadvantage of this circuit, and you might have already guessed it. The two complementary transistors need to be identical. Even though this is NPN and the other one is PNP, the electrical characteristics for both of them must be identical. So the main reason why this configuration cannot be used for class AB amplifiers is that the set of values of the resistors will only work for a particular push-pull configuration. Moreover, the set of values needs to be chosen very carefully, especially if the complementary transistors are different. This method is very similar to the voltage divider network. The only difference is that an adjustable resistance, or potentiometer, is placed between the two networks. The advantage of this solution is to closely match the biasing of the two complementary transistors with a controllable resistance, even if the transistors have different electrical properties. So again, the advantage of this adjustable biasing arrangement is that the basic amplifier circuit does not require the use of complementary transistors with closely matched electrical characteristics, or an exact resistor ratio within the voltage divider network, as the potentiometer can be adjusted to compensate. So this is the solution to the problem of having slightly different electrical characteristics of the two active devices. But there is another problem, which is probably even worse than this one. Let's go back to the previous circuit for the ease of understanding the problem. This problem is caused by the thermal runaway. So thermal runaway occurs in situations where an increase in temperature changes the conditions in a way that causes a further increase in temperature, often leading to a destructive result. It is a kind of uncontrolled positive feedback. Thermal runaway occurs because as the base emitter junction temperature increases due to self-heating as well as potential ambient temperature increase, the current through the transistor increases as well. So again, as the temperature of the transistor increases, the collector current increases as well, and the higher collector current means that the transistor will warm up even more. So both transistors, due to thermal runaway, will enter into a vicious cycle which will lead to destructive results. So how can we resolve this problem? One way to compensate for any temperature-related variation in the base emitter voltage is to use a pair of normal forward bias diodes within the amplifier's biasing arrangement. As you can see, a small constant current flows through the series circuit of R1, D1, D2, R2, producing voltage drops which are symmetrical either side of the input. With no input signal voltage applied, the point between the two diodes is 0 volts. As current flows through the chain, there is a forward biased voltage drop of approximately 0.7 volts across the diodes, which is applied to the base emitter junction of the switching transistors. So again, the voltage drop across the diodes biases the base of the NPN transistor to about 0.7 volts and the base of the PNP transistor to about minus 0.7 volts. Thus, the two silicon diodes provide a constant voltage drop of approximately 1.4 volts between the two bases, biasing them above cutoff. The trick starts from here. In real world, these two diodes are positioned right next to these two transistors, and most of the time these transistors are mounted on a heatsink. These two diodes are usually mounted on the same heatsinks as the output transistors, therefore when the two transistors heat up, so will the two diodes. So again, the diodes and the transistors are very close to each other, and also because they are on the same heatsink, as the transistor is heating up, the diode will be affected too, heating itself up as well.